Welcome everyone. In this video we are going to see how we can separate quadratic drag into its components. Now before quadratic drag, let's start with linear drag. For linear drag, and let me erase this. Alright, so for linear we know that the force of drag will be equal to negative k. K here is just a constant, a positive constant, times the velocity. This negative means the drag is opposite the velocity. So this is the linear drag, and we know if the drag force is like this, so let's even write it like that. If this is kV, the magnitude is kV, v without an arrow on top means the speed for our purposes, then we know we can separate it into its two components. This and this. If we choose x and y like that, then this will be kvx and this will be kvy. So this is the case for linear drag. What about quadratic then, which is the focus of our video today? So let me write quadratic drag. And by the way, it is really important to understand that quadratic drag is a better model while describing real world situations. Okay, the air drag is actually quadratic rather than linear. So it is really important that we understand how to deal with that. In this case, the force of drag will be, again, negative k, this time the square of the velocity, and to denote the direction, we will put a v hat. V hat is just a unit vector along the velocity, okay? And you can see where the name quadratic comes from. It comes from this square right here. So how could we separate this guy to its components? If we have the force like this, kv squared, it might seem reasonable that x would be kvx squared and the y would be kvy squared. Why not? And in fact, this is not correct. This does not work. But why doesn't it work, and how could we find a formula that works? Well, let's try to find one that works then. And when we find it, you will see that it isn't the same result, which would, of course, prove that this doesn't work out. So I want to start with the definition, this model that we have, and it won't take much time, trust me. So we have the force of drag is equal to negative k, the speed squared, and then the v hat direction. Well, we know that for the force of drag, it will have two components for our case, the x and the y. So we can separate it into its components then. This will be fx in the x hat direction plus fy in the y hat direction. Right, this is exactly the force of drag. We separated it into its components. We did not change anything. Now this will be equal to negative k v, and then we have v times v hat. What is v times v hat? Well, that is going to be the velocity. So we can simply write negative kv and then the velocity. Alright? Now, what about the velocity though? It is a vector, so it should have components. And then we can write it in terms of its components. Let's do that. Why not? We will have negative kv again. And for the velocity, I am now going to use its components. It will have a vx in the x hat direction and a vy in the y hat direction. And we need to close the parentheses here. Alright, so far so good. Now let's distribute the parentheses. I think I repeated. Anyways, so we will have negative kv vx x hat plus, well, rather a minus actually, minus kv Vy times y hat. And look at this. Look at this. For these two, for this and this to be equal, for them to be equal, corresponding components should be equal. That means whatever is next to x hat should be the same. So using that idea, we have f of x is equal to negative kv vx. And we have f of fy is equal to negative kv vy. That means, let me summarize this. Oops. Well, let's change that to black. Alright, so let me summarize what we just showed. We showed that if we have the force like this, kv squared, the quadratic drag force, then and we choose a coordinate system like this, x and y, then this component, the x component, will be kv times vx and kv times vy. Alright? I mean, this might be interesting, but we just showed that it is the case. We used components of vectors. And it is sometimes conventional to write this result as k vx plus vy squared under the square root vx, and this one as k under the square root vx squared plus vy squared, then vy. And this basically comes from the idea that if we have the velocity like this, vx and vy, from the Pythagorean, v squared is equal to vy squared plus vx squared. That means v is equal to vy squared plus vx squared under the square root, and it is positive because we are interested in magnitudes. Alright, so in this video we just talked about how we can separate, and by the way, also, this should be 90 degrees, of course, right? We are interested in the components, so these are 90 degrees. So we just showed how we can separate quadratic drag into its components. It is, I think, interesting because it might be counterintuitive at first, but as you can see, the math does not lie. I hope this video was helpful. If you have any questions, please add them in the comment section. I hope to see you in another video. Until then, take care.